What is a hypothesis? A hypothesis is a tentative assumption that is capable of being tested. It is a hunch, an educated guess, a proposition that is empirically testable. Scientific reasoning is based on 3 steps. 1. The proposal of a hypothesis or tentative assumption to account for a phenomenon or test the validity of some situation. 2. The deduction from the hypothesis that certain phenomena should be observed in given circumstances. 3. The checking of this deduction by observation and testing. Hypothesis testing is an inferential procedure that uses sample data to evaluate the credibility of a hypothesis about a population. Judging and stating hypotheses. Hypotheses should be stated clearly, in correct terminology, and be operationally defined. They may derive from theory, or from problems. They should be testable, so that they are capable of being either confirmed or refuted. A hypothesis that cannot be tested does not belong to the realm of science. Instruments should exist or be developed that provide valid and reliable measures of the variables involved. They can be tests, questionnaires, rating scales, interviews, scientific or technical measuring devices, and so on. Hypotheses should state the expected relationships between variables explicitly. They should also be limited in scope. Hypotheses of global significance are not required. Instead, precise, focused, and succinct hypotheses are preferable. They should be grounded in past knowledge, and be consistent with the most known facts. Hypotheses should use operational definitions. An operational definition is one that specifies or defines unambiguously in measurable terms. Hypotheses should be stated either in the form of proposed relationships, or in terms of comparisons, differences. The statistical tests used for each type of hypothesis are different, so we always need to know which type we are stating. A relationship hypothesis will use some type of correlation test, and a difference hypothesis will use, for example, a t-test, or analysis of variance. Testing hypothesis. Hypothesis testing is one of the most important concepts in research. There are 2 opposing possibilities when testing hypotheses. 1. The null hypothesis, H0, implies that nothing much happened. It is the assumption that any difference or relationship that exists between populations is due to chance. 2. The alternate hypothesis, H1, implies something exists or happened. It is the restatement of the hypothesis in the same terms as those used in the null hypothesis, expecting that the differences or relationships are assumed to be real, and not due to chance. When we test a hypothesis statistically, we are trying to see if something happened and comparing it against the possibility that very little happened. We are trying to disprove the null hypothesis. The null hypothesis is assumed to be true unless we find evidence to the contrary. If the calculated significance level is 5% or less, p less than 0.05, then we can reject the null hypothesis, that the difference in relationship is simply a chance one. If it is more than 5%, p greater than 0.05, then we retain the null hypothesis, as the result is probably due to chance. The null hypothesis does not say that there is no difference, or no relationship. It states that the difference or relation is such, that it would regularly occur only by chance. This is why we always use the words, no statistically significant difference or relationship. Statistics can never prove anything. All a statistical test can do, is assign a probability value to the results you have. The lower the probability that they reflect a random fluctuation, the more we have confidence that there is a real effect. Statistical errors. In performing a statistical test, you are usually looking for some results such as 1. A difference between means, as with a t-test or ANOVA. 2. A difference between proportions, with a chi-square. 3. A relationship, a correlation or regression. You can make an error or 2. Type 1 error. You might say things are significantly different when they are not. That is, reject the null hypothesis, when it is true. The probability of rejecting the null hypothesis is equal to the alpha level, significance level. Type 2 error. You may miss a significant relationship that really exists. That is the probability of accepting the null hypothesis when it is false. Type 1 errors are determined by the alpha level, and are therefore under the investigator's control. The greater the chances of a type 1 error, the less likely a type 2 error, and vice versa. Since the significance level is the same as the chance of making the type 1 error, the lower we set the significance level, the smaller the chance of a type 1 error. Type 2 errors can be avoided if we change our perspective from hypothesis testing to ways of measuring whether the treatment has had an effect. Effect size and power. A statistically significant t-test or p does not tell us how large an effect the variable had. Measures of effect size are used to determine the strength of the relationship between the independent and dependent variables. They reflect how large the effect of an independent variable was. They also provide information about the amount of impact an independent variable has had, and therefore complement tests of statistical significance. Measures of effect size can be used to summarize a series of experiments that have included the same independent variable and dependent variable, meta-analysis. This allows for a quantitative comparison of the outcomes across the series of experiments. Lastly, measures of effect size help us calculate the sample size needed for a study, with a particular level of power. Measures for estimating effect size include the standardized mean difference, D, correlation coefficients such as R and phi, and correlation ratio. Standardized mean difference, D, is a ratio that measures the difference between the means of the levels of the independent variable, relative to the within-group standard deviation. The Pearson product moment correlation or R, is an effect size in itself. It can be computed easily for most other statistical tests, by turning the statistic into a correlation. The chi-square statistic can be interpreted as though a correlation. It is always positive, as chi-square is always positive. To compute the effect size for analysis of variance, a correlation measure termed correlation ratio is employed. It is analogous to a correlation, but describes a curvilinear relationship rather than a linear one. When evaluating a study, you must consider first whether the result is statistically significant. You must then also consider whether the effect size is sufficiently large to make the result useful and interesting. Power of statistical test. Inferential statistics are designed to help us determine the validity of the null hypothesis. We want our statistics to detect differences in data that are inconsistent with the null hypothesis. The power of a statistical test is its ability to detect these differences if the research hypothesis is true, and the probability of making a correct rejection of the null hypothesis when it is false. The more powerful a statistical test, the more readily it will detect a treatment effect when one really exists. The concept of power and type 2 error are closely related, since the test can either correctly detect the presence of the treatment effect, or it can fail to do so. Difficulty in computing power stems from the fact that it depends both on the size of the treatment effect and sample size. When there is a large effect, power will be high. The influence of sample size on power. Sample size influences power because the larger the sample size, the smaller the standard deviation of the distribution of means. It is also the main way to modify a study, to bring it up to sufficient power. But sample size provides a major problem with correlation. If you include enough subjects, you could find statistical significance in even the most trivial of relationships or differences. For this reason, your sample should be large enough to be sensitive to relationships of differences, but not so large as to produce significant but trivial results. The power of your statistical test increases with the size of your sample, because larger samples provide more stable estimates of population parameters. The standard error of the means from your treatments will be lower, so the likely population means fall within narrower confidence limits. Thus, it is easier to detect small differences in population means, and to reject the null hypothesis when it is false. In this presentation, you have learned how to formulate and test hypotheses. You have also learned the importance of statistical errors, as well as the significance of statistical power. Further, you have learned about the measures of effect size and the influence of sample size on power. These statistical concepts build on the statistical foundation laid in Module 2, and prepare you for the additional statistical concepts introduced in the remaining modules of this course.